Hi, everyone. So we're going to work on week 3 of these worksheets. Let me get rid of this 4. And this worksheet is a lot of naming. In this first part, we're going to be kind of reviewing empirical formula and then percent mass. All right, so first question, I guess pre-question 1, says, what is the difference between molecular and empirical formula? Right, as we said in the last worksheet, the empirical formula is the most simplified ratio of elements, while the molecular formula is the actual ratio, or the actual observed ratio, whatever, right? So what you would actually see, right? Taking data in a lab, right? Finding the molecular mass, so using something like mass spectroscopy, which you'll learn about if you go into organic or analytic chemistry. So next, it says, where are the anions and cations typically found on the periodic table? What are other important parts of the periodic table? So on this left side, right, these are your typical cations, right, on the periodic table. Over here, actually, I should extend this. Over here, these are going to be your typical anions on the periodic table, and also selenium. Also, boron and aluminum are your typical cations, so we should include those with that side. Some other important parts of the periodic table, right, is your noble gases. They don't do anything, so if you see those in a reaction, they are inert, right? They're not going to react. The other important part is the transition metals, right? Everything pretty much down here. You're going to have to, we're going to look at those with naming, right? A lot of these transition metals can have different oxidation states. And so you have to make sure that you look at their oxidation states for different reasons, right? For redox reactions, for naming, and so on and so forth. So the anions are on the right side, right in the nonmetal section, and the cations on the left. All right, we're gonna go to percent mass. So it says determine the percent mass of H2O in the hydrate. So we have chromium nitrate, and then 9H2O, chromium 3 nitrate to be more specific. So again, what we did in the last worksheet, if you didn't see that and you're confused on this question, we did a lot of mass percent back there. This is very similar. So we're going to find the molar mass of chromium nitrate hydrate first. And then we're going to go ahead and take the mass contributed by water and divide it by the total, right? So here, let's go and check this, right? Chromium has a mass of 52. Nitrate, now there's 3 of them. I'm going to put a 3 on the outside, put this in a bracket. 3 times nitrogen is 14.01, right? We have 3 oxygens per nitrate, so 3 times 16. And then we have 9H2O. So we have 9 times, and then 2 times 1.008 for hydrogen, plus 16. All right, and then that is it. So we go ahead and we add these up. And this ends up being 400.174 grams per mole in total. Right. So that is for the whole compound. Now I'm going to just look at the water for this next part, right? So 9 times H2O, right? The molar mass. What is that? I have it at the end here, right? It's 9 times 2 times 1.008 plus 1 oxygen. And we end up getting 162.144 grams per mole. And now we're just going to go ahead and take the mass contributed by water, right? Divide that by the total mass. So 162.144 grams per mole over 400.174 grams per mole. That is equal to, oops, and I almost forgot, times 100%. Yeah, it should end up getting 40.52%, and that is your answer. So the percent by mass, right, water is 40.52%. All right, next question here. It says empirical formula. The food flavor enhancer for monosodium glutamate, MSG, has the composition of 13.6% sodium, 35.5% carbon, 4.8% hydrogen, 8.3% nitrogen, and 37.8% oxygen by mass. So what is the empirical formula? So in the last worksheet, we did similar questions, and it actually is going to be the exact same procedure. All right, we're going to consider 100 grams of substance or of the compound. And then we're going to go ahead and turn these all into moles, right? So 13.6% is 13.6 grams, right? These are all percent by mass. Convert all these to moles for their respective elements, and then divide by the smallest moles here. So I'm going to speed through this one, right? Since that last worksheet, if you want this more done in depth, I would go check that. Here I'm going to speed through this so it doesn't take too long. All right, so for sodium, let me label all these. So for sodium, right, out of 100 grams, we have 13.6 grams. Sodium is about 23, it's 22.99. 22.99 grams of sodium for 1 mole, right? I'm using the molar mass here. We end up getting, oops, 0.59. I'm just going to leave 3 decimal places. It should be sufficient for when we divide everything at the end. And moles of sodium. Next, 35.5 grams of carbon. This is for carbon. So 35.5 grams of carbon. Carbon has a molar mass of 12.01 grams of carbon for every 1 mole of carbon. Go ahead and divide these out. Right, and again, it goes without saying that these all cancel out, right? That's why we're doing this. All right, 2.956 moles of carbon. We're going to go to the next one here. Hydrogen. So we have 4.8 grams, whoops, of hydrogen. Then we're going to go ahead and convert this. We have 1.008 grams of hydrogen for every 1 mole of hydrogen. We end up getting 4.762 moles of hydrogen. Now we're going to go ahead and do nitrogen. And we're just doing the same thing for all of these. Out of 100 grams, how many moles do we have of each element? Nitrogen is 14.01, and you can check your periodic table for these. For every 1 mole of nitrogen, 0.592 moles of nitrogen. And then last but not least, we have to do oxygen. So for oxygen, we have 37.8 grams. There's a 16 grams of oxygen for 1 mole. And you get 2.3625. All right, now we have to divide all of these by the smallest amount of moles, right? So we can get a nice ratio to one another and write our empirical formula. So the smallest one here is 0.592. So I'm just going to go ahead and divide all of these by 0.592. So for sodium, right, this is just going to be 1. For carbon, 956. Again, if you're having trouble with this, I would check the last worksheet that we did. I explain a little bit more as to why we do this. This is about 5, right? We're just going to round to the nearest number within reason, if it is within reason. This is 5 moles of carbon. Next, we have 4.762 moles of hydrogen. We take that. This is about 8 moles of hydrogen. Now I have to do nitrogen, right? Nitrogen is the same as carbon, number-wise. So that's 1, or I should say about 1, since when they were decimals with all their numbers, they were not the same. And sorry, I shouldn't have said carbon. I meant to say same as sodium, right? Those are the same, 0.592, about the same, if I didn't round. And then last for oxygen, 2.363 moles of oxygen. .592. This is about 4 moles of oxygen, right? So now this is nice, right? This is essentially telling me for every 1 mole of nitrogen, I have 5 moles of carbon, I have 8 moles of hydrogen, 1 mole of nitrogen, 4 moles of oxygen, right? You can also, this is the same with atoms. So for every 1 atom of sodium, I have 5 atoms of carbon, 8 atoms of hydrogen, 1 atom of nitrogen, and 4 atoms of oxygen. So our empirical formula is going to be NaC5H8NO4, and that's it. All right, we're going to move on to 3 here. So it says the element X forms the XCl4 containing 75.0% chlorine by mass. What is element X? Okay, so first what you want to do is find the total mass, right? And then you can figure out what element X's mass is, and then figure out what element it is. So how do we do that, right? So it's telling you that chlorine is 75% by mass. So let me actually go ahead and write this out, right? If I were to write the formula here, the mass of chlorine over the total mass times 100%. I'm not going to use an X here just because we have an element X, is equal to 75.0%. Right, that's our general formula that we've been using. Now I do have the mass of chlorine, right? They tell us what the formula is. They tell us that it's XCl4. So the mass of chlorine is just the chlorine mass times 4, right? There's 4 of them, 35.45 times 4. Right, this is 141.8 grams per mole. Again, there's 4 chlorines. So, and maybe I should label this a bit better. So for 4 chlorines, all right, you get 141.8 grams per mole. All right, now let's go ahead and find the total mass here. So I'm just going to plug this number in, 141.8 grams per mole over total mass, or molar mass would be more appropriate, times 100% is equal to 75.0%. And then I'm going to solve for total mass here, right? So you should end up getting the total mass, skipping a little bit of algebra here, but it should end up being 0.75 divided by 141. Oops, no, other way around. 141.8 grams per mole over 0.75. Right. You go ahead, divide each side by 100%, you get 0.75. Multiply the total mass to both sides to get it out of the denominator, and then divide both sides by 0.75. Okay. So if you're having trouble with the algebra, try considering this as some variable, like W or something. I'm not saying X because that's our element. All right, so now what we can do here is just, again, plug this in. So the total mass ends up being 189.067. Now, why is this important? Because this tells us what the total mass is, right? Where we can take the chlorine mass, subtract it from here, and find what the mass of just element X is. So we're going to find the element X weight, right? I'm going to go ahead and let me actually write a formula here in case it's helpful for anyone, right? The formula here is the mass of X plus mass of chlorine equals the total mass, right? So all I have to do is subtract chlorine mass from both sides. And we have the numbers here, right? Our total mass is 189.067 grams per mole. Let me try moving all this up. I think it would be a little bit neater. One second. Right, and then I'll just note that's some algebra. Let me have this. All right, so mass X is 189.067 minus 141.8 grams per mole. And we end up getting 47.27. I'm just going to do 2 decimals, grams per mole. So let's see what element weighs 47.27 grams per mole, or what is closest to it at least. Right, so what is closest? Let's see. This is 44, this is 50, this is 47.9. I know it's quite a bit off, but it is the closest one here. So our mystery element is closest to the weight in titanium. So we know that this is titanium. And say the titanium mass is closest. So X is equal to titanium. you want to be really specific, you could say titanium 4 because of the oxidation state. Okay, so we'll go on to the next one here. We're going to move on to oxidation states. So it says indicate the oxidation state of the underlined elements. Remember that there are exceptions. So for letter A, right, it says CH4. Hydrogen is typically a +1. We're going to see an exception here. It's typically a +1 unless it's paired with a metal, right? Specifically an alkali metal or an alkaline earth metal. So we're going to assume hydrogen is a +1 here, right? So if all these hydrogens are +1, and there's 4 of them, they contribute a +4 charge, right? The carbon now has to balance that charge out because this is a neutral molecule, right? It's a 0 charge. You don't see a minus or a plus. So the carbon has to be a -4 oxidation state. Okay. Otherwise, you would have some sort of charge if they were not equal. Okay, so B, it says sulfur tetrafluoride. So same thing here, right? We're going to assume fluorine is typically a -1. So we're going to assume fluorine is -1 here. So there are 4 fluorines, they're all -1. So they contribute a -4 charge, which means that the sulfur has to be a +4 charge. Remember, this is neutral. I don't see any charge there, right? There's no minus, no plus. All right, we're going to go to the next one here. Sodium oxide. So sodium is always a +1. So for your alkali metals, right, hydrogen is a non-metal. For your alkali metals and your alkaline earth metals, those are always going to be +1 or +2. You'll never see those as like a -3 or anything else. Okay, so we're going to assume sodium is +1 here. Oxygen is typically a -2. However, if you assume that, you're going to get this wrong. So typically a -2, not always. Sodium here has to be a +1 though, as I just said, right? So these are both +1. There's 2 of them, and these go ahead and contribute a +2 charge. The oxygens, there are 2 of them, right? So each oxygen has to be a -1, right? +2 divided by 2 is equal to 1. Now, it has to be a -1, right? Because the oxygens have to be the opposite charge. So I should have actually put -2 divided by 2, right? That's the charge. It has to be offset to get a neutral molecule. So it's -1. All right, next is KMnO4. So again, we're going to have to assume some things here. We're going to assume oxygen is normal this time, right? Not a -1, but a -2. If you can't assume these things or you don't assume them, you're not going to be able to do these problems. So in this case, we're going to assume oxygen is a 2- or a -2, potato, and potassium is going to be a +1. Again, this is a neutral molecule, so just keep that in mind. We don't see a charge here. So if potassium is a +1, the oxygens are all a -2. Oops, and there's 4 of them. Right? We add these up, and we have a -7 charge in total. Right? So the manganese has to offset that and has to be a +7. Right? If there was a +1 charge, it would be +8. If it was a -1, it would be 6. We're going to see some examples here. But it's neutral, right? So they have to be equal in charge. You have to offset that -7 charge with a +7 for a neutral molecule. All right, next we're going to look at platinum, or platinum with this whole compound. So water, check the oxidation state, right? Both of these, or all 3 of these, so we have 2 times +1. We're going to assume oxygen is a 2-. plus -2, and you'll find that this is a 0. Right, so all these waters are 0. Right, we don't have to worry, they don't contribute any charge. So let's look at the ammonium. So over here, this NH4, right? Each one of these, so you actually should know this by heart. Nitrogen is typically a -3, H is typically a +1, so this has a total charge of +1. You can do that, but you also should just know this by heart. So this is 2 times +1 because we have 2 of them. All right, so these contribute a +2 charge. Now, if we're looking at this, right, you have a +2 charge, but the net charge is a +4. So the platinum has to get us to +4, or 4+. To get us to 4+, right, the platinum has to be a 2+. And just to keep everything consistent, I'm going to put the plus after and the minus after. Which doesn't really work out if you're doing this addition and subtraction math. It's just a notation thing. So platinum has to be 2+, again, to get us to that 4+, right? The ammonium gives us +2. The platinum has to give us +2 more to get us to the 4+. All right, next is this molybdenum, and then these hydroxides, and this ammonia. So NH3. So we're going to look at everything else, right? Hydroxide is a -1. Oxygen is typically a -2, hydrogen a +1. So it's going to be -1 for each. You should also just know this by heart. So OH is 4 times -1. There's 4 of them. So this contributes a -4 charge. Right? And again, the reason I'm writing the negative in the beginning is because math doesn't really work out unless you have the signs in the correct spot, right? You can't really put the minus after. Just a convention thing. In chemistry, to put the plus or the minus after when you have stuff like this, 2+. All right, next is going to be the ammonia. This is a 0, right? It's going to equal out. Each nitrogen is a -3. Hydrogen is +1. It equals out. All right, so we have this molybdenum. Right now we have a -4 charge. We have to get to a +2. So this molybdenum, right, and we have to actually split this between 3 molybdenums. So what we're going to do is this, right? We have actually, let's do it like this. 2 minus -4. That's 6. So what does this mean? The charge has to be +6 contributed by 3 molybdenums. Right? So if I have to split this between 3, then each one has a +2 charge, or 2+. Again, just naming convention for where the sign goes. All right, last one here. It says you have magnesium hydride. So hydrogen is typically a +1. Not always, though. Typically. Although magnesium is always a 2+. So these hydrogens have to be a -1 each, right? This is a +2. Both of those have to be a -1 to balance that out. Again, these are the exceptions to the rule, not the rule. So, or not the norm, I should say. So magnesium hydride is -1 for the hydrogen. All right, so we're going to get into the nomenclature part of this worksheet. So for the first one here, right, we have HClO2. So you have different series of polyatomic ions, right? So you would want to memorize that, right? So typically, like if you have 2 items in a series, right? So let's say like SO3 and SO4, the one with more oxygens is going to end in ate. The one with less is going to end with ite. So SO3 is sulfite, SO4 sulfate, right? NO3 and NO2 respectively are going to be nitrate and nitrite. When you have more than two, it's where it gets a little tricky. So, right, the chlorite 8 series, I guess. It's where it's a little tricky. So for chlorine, right, ClO2 is chlorite. ClO3 is chlorate. Now there's also ClO4 and ClO. So ClO4, when it goes past that middle, I guess, biggest one, that one you have to put a per in the beginning. So perchlorate is ClO4, right? Chlorate is ClO3, chlorite is ClO2. Then if you go one oxygen less than chlorite, it's going to be ClO, or sorry, ClO, which is hypochlorite. You're gonna have that hypo in the beginning. So when you name these, what you're going to want to do is name them with the conventions that you did in class, right, on that worksheet. So we have a hydrogen in the beginning, so we're going to want to denote this as an acid instead of just writing like hydrogen chloride. So over here, right, we have HClO2. I'm going to call this some sort of acid. This is going to be chlorous acid. So if it ends with an ite, you're going to put an OUS, so chlorus, right? Instead of chlorite, you replace the ite with OUS, us. And then the acid indicates the hydrogen in the beginning. So chlorous acid is going to be HClO2 here. All right, next we have H2SE, right? We have two nonmetals here. Hydrogen is a nonmetal. So this is dihydrogen selenide, right? So you have two hydrogens, indicate it with a dihydrogen, and then the selenide is the Se, right? You can check your periodic table here and confirm that these are both nonmetals. I know hydrogen's in the metal section, the alkali metals, but it's the nonmetal. Everything below it is a metal though. All right, so we have dihydrogen selenide. Now we have HNO2, right? This is going to be nitrous acid, right? NO2 is nitrite, but we have that H in the beginning, so this is going to be nitrous acid. Can I go to the next page? All right. We have SRO, so strontium, right? Is that a nonmetal or a metal? We can see here it is a metal, right? So we have one metal and one nonmetal. All you have to do here is name this strontium, so the name of the metal. And then you take the first part of the other element, the nonmetal element, so ox, and then ide. The strontium oxide, fluoride, right, is another one, and so on and so forth, right? Bromide, iodide, etc. All right, E, it says we have K2CrO4. So the K2CrO4, the K is potassium, right? That is a metal in group 1. I'm just going to name that as normally. And the CrO4 is polyatomic ion. It's a transition metal, polyatomic ion, and this is chromate. So this is potassium chromate. All right, next we have Cr2O3. So Cr2O3, right? Chromium is a transition metal here. So you have to make sure to label its oxidation state, right? There's a lot of transition metals, not all of them, but many of them have different oxidation states. So chromium and then oxide, right? Now, we have to label what is the oxidation state. So I'm going to leave a space here. So each of these oxygens are a -2 charge, right? And that ends up being a -6. Each of these chromiums right? They have to together balance out that -6, right? So each chromium has to be a +3 charge. So this is going to be chromium 3 oxide, right? You would indicate it with Roman numerals here. So chromium 3 oxide indicates it's a chromium +3 with oxygens. All right, next we have this iron something sulfate. Again, iron's a transition metal right over here. So let's go ahead and indicate exactly right what oxidation state it is. So I'm going to, again, just write this out. Iron, this is sulfate, not sulfite, right? This is SO4. And then we're going to figure out the oxidation state. So SO4 typically has a -2 charge or 2- charge, and there's 3 of them. So 3, there's a -2, right? These contribute a -6 charge all together. So if those contribute a -6 charge, the iron, there's 2 of them, they have to offset that -6 charge, right? This is going to be iron 3 sulfate, right? These both have to be a +3 because this is neutral. All right, next we have NH4, HPO4. So in this last one, we have a whole bunch of nonmetals, right? We have two polyatomic ions actually, and then the nonmetal of hydrogen. So the way we're going to name this is first we have this ammonium, right, polyatomic ion, and there's 2 of them. So I'm going to indicate this with di. So diammonium. Oops, I forgot an M here. Diammonium. And this is hydrogen. And then the PO4 is our phosphate. That's it. So diammonium, hydrogen, phosphate. Right? Why didn't I put this into some sort of acid form? Because it's not an acid here, right? It's not just H and then some other polyatomic ion, as how you'll typically see it. All right, number 6, it says write formulas for the following compounds. So we have lead 2 perchlorate, right? So we know lead is Pb and it's a +2. Perchlorate is a ClO4. So perchlorate has a -1 charge. And then I'm going to go ahead and just write the formula. I need these charges to balance out. So I know that lead is a 2+, right, from the lead 2 part, specifically the 2 part. And then I have ClO4, and there has to be 2 of them, right? Each of them are a -1. These charges are things that you're just going to have to remember. So we have lead 2 perchlorate, sorry. So yeah, 2 perchlorates to balance out the +2 charge from the lead. All right, next we have hydroiodic acid, right? This is just hydrogen. The iodine is the iodic part. This is HI, right? This is going to be one of the strong acids you should remember. So hydrochloric, hydrobromic, hydroiodic. All right, next C is going to be chlorous acid, right? We did this one. So chlorous acid, right? You're replacing the ite in chlorite with an OUS. So we're just going backwards here. So this is ClO2, and the acid part indicates the H, right? So this is H, ClO2. All right, as we saw up here, oops, on the other page, this is what we got. Right, so ClO2 has a -1 charge. All right, next is sodium hydrogen sulfite. So this is sodium, that is hydrogen, and then sulfite is SO3, right? Let's put the charges here. So sodium is a +1, hydrogen is a +1, and then sulfite is a 2-. So I'm gonna write this out, NaHSO3. Right, so You can look here and see the charges are balanced. So I don't have to worry about changing it like to 2 sodiums or 2 hydrogens or anything like that. All right. All right, next we're gonna go ahead and go look at E. It says dinitrogen tetraoxide. So dinitrogen, right? This is nitrogen, this is oxygen. Di means 2, right? So we have 2 nitrogens, and then tetra means we have 4 oxygens. F is a disulfur dichloride. So this is S2, again, di for 2. And then dichloride means I have 2 fluorines. So we're looking at balancing equations now. It says balance the following equations. So first thing I'm going to do, looking at this, right? We want to balance the elements that are by themselves. So over here, right on the right side, we have 2 things with phosphorus, and then there's phosphorus over here. It's usually easier to balance, again, the things that are not in 2 spots at once. So I'm going to balance the hydrogen first here. Okay. So looking at this, these hydrogens, right? I want to balance these out. So what is the least common multiple of 4 and 3? Right, that'll be 12. So I need to get these to 12, right? I need to use whole numbers here. I need to use integers, positive integers. So this has to be 4 and this has to be 3, right? 3 times 4 gives me 12 hydrogens on the left. 4 times 3 gives me 12 hydrogens on the right. Now let's worry about the phosphorus. So on the left here, I have 6 phosphorus. On the right, and let me write this down. There's 6 phosphorus over here. Oop. On the right here, I have 4 phosphorus from this one and 4 from this one. Now I can't change this one, right? This one's kind of locked in with that number that I put. So how do I get the correct number of phosphorus, right? So if I'm looking at this P4, I need 2 phosphoruses, right? Doesn't really pan out so nicely, right? I would need to cut this in half, right? I need 2 more phosphorus, but I can only get it in multiples of 4. What I'm going to do is actually just put this as 1/2 right now. This is not right. You can't take half of a molecule. However, this will indicate to me, right, that I need to take this whole thing and multiply it by 2. Right, so the phosphoruses are balanced, but I need whole integers, right, is essentially what is going on. Right now I have 6 phosphorus on the left, 6 on the right, but these aren't balanced correctly. So I'm going to multiply everything by 2, every coefficient by 2 specifically, and I'll get this 6p2H4. It gives me 8pH3 plus 1p4, right? You wouldn't actually put this 1, so I'm just going to erase it. I just want to make it clear. And now I have the right answer, right? This is the balanced equation here. So don't be scared to use fractions to balance it out, right? You can sort them out at the end by multiplying by the denominator. It's usually going to be 2, sometimes maybe 3. Okay, so we'll go on to the next one here. B, it says magnesium, or MgN2, so just magnesium nitrate, or magnesium nitride plus water, using magnesium hydroxide plus ammonia, NH3. So we have magnesium nitride, right? We're just going to balance this out. Let's see, what's easier to balance? It's probably easiest to balance the nitrogen here on both sides. So I'm just going to do that, right? So I'm going to stick this at a 1 so that doesn't fluctuate in number. And then I'm going to go ahead and put A2 here. Right? I want to balance the nitrogens first, right? You could do the magnesiums first too. That would honestly work fine. So I have 2 nitrogens on the left and 2 on the right. Now, let's check if my magnesiums are balanced, right? I have 3 on the left, 1 on the right. So I'm actually going to put a 3 here, right? I want the magnesiums balanced. Now let's go ahead and check our hydrogens and oxygens, I guess. You got to do these at the same time. So on the left here, I have 2 hydrogens. On the right, I have 6, right? Because there's 2 of these per magnesium hydroxide, and there's 3 in total. So I have 6 hydrogens here, and then 6 from here. So I have 12 in total. So I would have to put a 6 here to balance the hydrogens. Now, you could also do the same for oxygen. Let's check. So on the right here, I have 6 oxygens, right, just from this one. And I also have 6 oxygens here. So this works out, right? It is balanced. Okay, so for this next one, this one is a lot more difficult in terms of balancing. If you just try to balance each side normally, right, trying to just plug in the numbers and get them to work out nicely, it's not going to work. You have so many components here that in odd ratios in the end that you're not going to just get it to work out. So what I'm going to do here is write in the answer, right? And then I will have the work at the very end of this video, because I don't think this is something that you're really going to be tested on for how long this is going to be. But I want you to have access to it in case you do want to know. So this one is a 2. This one is a 10. This one is an 8. This one is a 6. This one is a 2, a 5, and an 8. Again, I will do this at the end of the video for any of those who are curious. All right, we'll go to number 8 here. It says, write balanced equations based on the information given. It says solid magnesium plus nitrogen gas gives you solid magnesium nitride. So how do we do this, right? You just write these out. So first we have solid magnesium as such, right? Not 2 plus. It's not aqueous. It's not an ion. It's just magnesium, right? Magnesium solid plus nitrogen gas, right? And I should actually be better here. N2, right? Gas, right? Nitrogen is diatomic. Gives you solid magnesium nitride, right? So we have MgN. Now I have to put in the subscripts here, right? So magnesium is a 2 plus charge, right? Nitrogen is a 3 minus. The least common multiple of 2 and 3 is 6. So I need 3 magnesiums to get to a +6 and 2 nitrogens to get to a -6 to balance these charges out. All right, now that I have that, I just have to balance this equation. This is a solid here. I just put a 3 here for the magnesium and it's done. All right, 2 nitrogens on the left, on the right, 3 magnesiums on each side. All right, B, it says solid sodium hydroxide plus solid ammonium chloride. Turns into solid sodium chloride plus gaseous ammonia plus water vapor. So and start in the beginning. So we have solid sodium hydroxide, right? Sodium hydroxide is NaOH. Solid ammonium chloride. So ammonium chloride, this is NH4. Cl, again, this is kind of grouped up. Don't have to write that, but it is NH4Cl. Right, this is also a solid. We're going to indicate that with the S in parentheses. This turns into solid sodium chloride. So this is NaCl, right? Plus gaseous ammonia, right? Ammonia, not ammonium, but ammonia is NH3. It's a gas. And then water vapor. So vapor just means gas, right? This is H2O as a gas. Okay, so now let's go ahead and balance this equation, right? So right now I have 1 sodium on each side, so that's good. I have 1 chlorine on each side, So that's good. Now I have 1 oxygen on each side. So that is good. And then let's check the hydrogens. I have 5 hydrogens. I have 3 plus 2, 5 hydrogens. So this is actually balanced already. All right, so that's it for 8B. Number 9, dilutions. What are the molarities of the following solids when dissolved in water? So you have 57.5 grams of CH3 and then 2 CO in a 525 milliliter solution. So the formula you're going to use is this. Molarity, or the concentration, is equal to moles over liters. So first we have to convert this into moles, is essentially what is going on. So you start with grams, need it in moles, and then we do have the liters, right? You can convert from milliliters to liters. So from grams to moles, 57.5 grams of this guy right here times, and then we're going to find the molar mass, right? So CH3, we have 3 of them. That's 3. Pretty sure this is just acetone, actually. Yeah, so this is acetone. So we have 2 times. 2 times the mass of CH3. So C is 12.01. Right, hydrogen is 1.008. So there's 3 of them. 3 times 1.008. And then I have another carbon and I have an oxygen that weighs in at 16. So the molar mass here should end up being 58.078 in grams for 1 mole of acetone. And then that converts this into moles. Right, you can go ahead and convert this into liters right now if you prefer the horizontal multiplication. I'm just going to write this out really quick for any of those who like the formula. All right, so this ends up being 0.99 moles of acetone. And then we're going to go ahead and divide this by the liters, right? So moles, then divide by liters. So 0.99 divided by 0.525 liters, right? That's what we're given. And that is the molarity here. So if you're just doing this in horizontal multiplication, right, your final unit, you're going to want it in moles over liters, right? That is the unit of molarity. So you could keep multiplying and then put it 1 over liters for the next step, right? So you would multiply by 1 over 0.525 liters, or you can plug into the formula. It's whatever your preference is. So I'm going to go ahead and plug this in here. This ends up being 1.8. How many sig figs? Let's use 3. 1.89 times, oh, no, that's it. I was going to say times 10 to the 0 power, but that's it. 1.89 molar. So convert your grams into moles first, and then divide it by the liters of solution that it's in. And that's how you find the molarity. Right, make sure it's in liters, not milliliters. Okay. For part B, it says we have 18.5 milliliters of C3H5OH3 with that density and 375 milliliters of solution. So we're assuming, again, that the whole solution is 375 milliliters. So for the molarity calculation, we're going to use 0.375 liters. So we're given the density here, but we need moles for concentration, right? So first I'm going to go ahead and convert from density and volume to mass so I can get the grams. So the mass is equal to density times volume, right? The density is 1.26 grams per milliliter, and we have 18.5 milliliters, right? We do see that the milliliters cancel out, so these are in the correct units. multiply with, and then we end up getting 23.31 grams, right, of this substance, C3H5OH3. Now we have to convert this into moles, right, and then into molarity. So 23.31 grams. I'm not going to write the whole thing. And just for the sake of room here, really more than anything, but this is grams of this substance. So the molar mass here, right, we're going to end up getting, let's see, so 3 times 12.01 for the carbons, plus 5 times 1.008 for the hydrogens, plus 16 plus 1.008 for the hydroxides, and you have to multiply that by 3 because there's 3 hydroxides. So technically they're not hydroxides, they're actually alcohol groups. You'll get there, learn about that in organic chemistry. But you have 92.094 grams for 1 mole. All right, now this is in moles. Now we go ahead and divide these. You end up getting 0.253 moles of C3H5OH, parentheses 3 for those OH groups. Now I have to take this and divide it by the liters of solution. So 0.253 over 0.375 moles over liters. And your molarity ends up being 0.675 molar, right, or moles over liters. That's your concentration. All right, number 10, it says determining the limiting reagent. How many moles of NO can be produced in the reaction of 3.00 moles of NH3 gas and 4.00 moles of O2? The reaction is not balanced. So first thing we're going to want to do is balance this reaction. We can see here, so first let's look at the nitrogen. So we have 1 nitrogen on this side, we have 1 nitrogen on this side, so let's not worry about it. Next thing is we have these oxygens. We have 2 oxygens here and 1, 2 here, right? So let's not worry about that right now. So let's look at the hydrogens. We have 3 here and 2 here. That's not balanced. So let's go ahead and use the least common multiple of both those hydrogen subscripts, right? So 3 and 2, right? The least common multiple is 2. Or sorry, 2 is 6. So we're going to multiply this side by 2 and this side by 3. Right, so I have 6 hydrogens on each side. The least common multiple of 2 and 3 is 6. So I want 6 hydrogens on each side. All right, now again, let's check our balancing. So hydrogens are balanced, but now I have 2 nitrogens on this side and only 1 on this side. So I'm going to go ahead and add a nitrogen here. Multiply that by 2. Now I have 2 nitrogens on each side, right? That is good. Next thing is let's check the oxygens. I have 2 oxygens on this side from this one. I have 3 from here, so that is 5 in total. And I only have 2 here. So this is O2. So 2 times what gives me 5? 5 halves. Again, this is not what we like. We don't like fractions because you can't take half of an O2. So I'm just going to take everything and multiply it by 2, right? Fractions will sort it out if you just multiply everything by 2. So multiply everything by 2 here, right? This first one ends up becoming 4. This next one becomes 5, right? 5 halves times 2 is 5. This is 4, and then this is 6. All right, now this is balanced. So now we can actually do this problem. It says how many moles of NO can be produced from the reaction of 3.0 moles of NH3 gas and 4.0 moles of O2. So first thing I like to do is first put this into moles of reactions. How many times can I do this reaction? Right. So we have NH3 and O2. So the way you want to look at it is this. So I have 3 moles of NH3. That's what I start with, right? And how many reactions can I get out of this, right? So for every one reaction, right, you can think of this as a recipe book, right? For every loaf of bread, I don't know, you use 1 cup of flour and 2 eggs. If you have 4 eggs, right, based on your eggs, you can make 2 loaves of bread. If you only have 1 cup of flour, you can only make 1, right? So your limiting reactant is your flour. So same thing here, right? The way we're going to look at this is for 3 moles of NH3, right? I need for every 1 reaction or 1 mole of reaction, I need 4 moles of NH3. All right, where did I get the 4? I got the 4 from here, right? That is the coefficient. So this 4 is the coefficient. That tells me, again, how many NH3s do I need per reaction? Again, remember, moles and number of atoms are linked together through Avogadro's number. So that's why I'm not talking about this in terms of number of atoms, since they are proportional. So I go ahead and do this, and then this tells me that I get 0.75 moles of reaction. So I can do this reaction at 0.75 mole amount of times, right? Mole being 6.022 times 10 to the 23rd. All right, next, right, I have to look at O2. So for O2, I have 4.00 moles. And then for every 1 reaction, I have 5 moles of O2 that I need to use. So you go ahead and divide that and you get 0.8 moles of reaction. Now this one is smaller, right? 0.75 is less. So that means that we're going to pick the one that you can do less reaction with, right? It's limited by the one that can that you just don't have enough of. So NH3 here is the limiting reagent. Right? You can't get as many reactions with what you have. Just like I said, with like a cup of flour and 2 eggs for a piece of bread, if you had 1 egg and 1 cup of flour, then you can only make half a piece of bread, right? You're limited by your eggs. So we have 0.75 moles of reaction from this. Now there's 2 ways you could do this. You could do stoichiometry, right? You could say, well, NH3 and NO are in a 1-to-1 ratio. So you get 3 moles of NO. Or you could go ahead and then use this moles of reaction. Either way works. I'll show both. So if you're using this, again, for this mole of reaction, right, for every 1 reaction or 1 mole of reaction, I get 4 moles of NO. Right, so then it just ends up going back to 3 here. Okay, so you get 3 moles of NO, right? The other way you could do it is this. You could do 0. Oops, not 0. You could say 3 moles of NH3, right? And in every reaction, and this is your stoichiometry. So for 3 moles of NH3, or sorry, 4 moles of NH3. So for every 4 moles of NH3 used in this reaction, I get 4 moles of NO. right? And then you still end up with 3 moles of NO. So either way works, however you prefer to look at it, using your stoichiometry, right? Going back, and then, I mean, it's still a form of stoichiometry, right? With the reaction. Okay. So that's it for 10. 11 says silicon carbide, SiC, is on the hardest substances known, making it valuable as an abrasive. It is made by a high temperature reaction of silicon dioxide with carbon. If SiO2 plus carbon gives you SiC and CO. It does not look balanced. So it says determine the limiting reagent when a mixture of 5.00 times 10 to the third grams of silicon dioxide, okay, and carbon react. So first thing you want to do again is balance this. So if we're looking at silicon, it is balanced. If you're looking at oxygen, it's not balanced. And if you're looking at carbon, it's also not balanced here. So I'm going to balance the oxygens first. I'm going to put a 2 there, 2 on the left, 2 on the right. And then now I have 3 carbons on the right. So I need 3 carbons on the left. So that's actually fairly easy to balance. All right. Now we have to go ahead and do this problem. So first thing you want to do is convert these to moles. You cannot work in grams when you're working with these reactants. You have to work with moles. Because different grams, depending on how big the molecule is, they weigh different amounts. You look at these reactions not based on their weights, but by how many you have, right? In terms of moles, or which is what we work with, or in terms of atoms, which basically nobody does. But yeah, they are linked by Avogadro's number. So what we're going to do is first convert these to moles. This is 5.00 times 10 to the third. That's annoying. I'm just going to write 5,000. So 5,000 grams of silicon dioxide. And let's convert this to moles, right? So silicon dioxide, silicon weighs 28.09. There's 2 oxygens, and each weighs 16, so 32. This ends up being 60.09 grams of SiO2 for every 1 mole of SiO2. All right. So that's it for that one. All right, we just go ahead and get rid of those. And then actually, you could convert this to moles. Let's do that. I was going to just convert it to moles of reaction, but again, I think most people are used to just normal stoichiometry. So I'm going to keep this in moles of silicon dioxide here first. Give me 1 second here. This is 83.209. So we don't have any rounding errors or big rounding errors. And moles of silicon dioxide. Now I do want to divide this by the coefficient. All right, moles of silicon dioxide. Right, it is 1-to-1. So for every 1 mole of silicon dioxide, I get 1 mole of reaction. So still 83.209 moles of reaction for silicon dioxide. All right, for this other one, right, this is 5,000 grams of carbon. Convert this to moles first, right? There's 12.01 grams of carbon for every 1 mole of carbon. Right, these cancel out. Get 5,000 divided by 12.01. Get 416.32 moles of carbon. All right, and then let's go ahead and convert this into moles of reaction. So 416.32 moles of carbon. Now, for every 1 mole of reaction, or every time I do a reaction, I need 3 carbons from our balanced equation. Those cancel out. And then let's see what we get. Get 138.77. All right. Now we can see that the silicon dioxide is smaller, right? You get less reactions out of the silicon dioxide. There's excess carbon or not enough silicon dioxide, I guess, on how you look at it. But this is the limiting reagent. So using stoichiometry, right? I have, can I move this up really quick? Using stoichiometry, I have 83.209 moles of silicon dioxide. I want moles of this SiC, so silicon carbide. So it is in a 1-to-1 ratio, right, in this balanced reaction. So for every 1 mole of silicon dioxide, I get 1 mole of silicon carbide out. And we end up with 83.209 moles of SiO2. Now, this is not what we want, right? So I'm actually going to extend this. Let me move this back. Right, we want not the moles, but we want the grams. So I have to convert this into grams of silicon. Oops, I meant to say silicon carbide. Right, silicon weighs how much? Silicon weighs 28.09. Let me write this in, 28.09. Right, carbon is 12.01. So you add them together, you should get 40.1 grams of silicon carbide for every 1 mole. And then you should end up getting 2.07. Wait a minute. Moles, oops. These are upside down. All right, so the answer is off. Sorry, it should be multiplying by the molar mass. So 40.1 grams over 1 mole. Sorry, so 83.209 times 40.1. We end up with 3,300. We're going to use 3 sig figs here. So 3,340 grams of silicon carbide. Okay, and that is your answer. Now for this next one, it says how many grams of excess reactant remain after the reaction is complete? So we're looking at this, right? How do we figure out how much carbon was used, right? These aren't in a 1-to-1 ratio. It's in a 3-to-1 ratio. So what I can say is for every mole of silicon dioxide used, right, using stoichiometry, I know that there are 3 moles of carbon used up in this reaction. So let's see how much gets used. Right, so 249.627 moles of carbon are used, right, or used up. So now I'm going to go ahead and subtract from how many we actually had. We had 416.32 moles of carbon. And we end up getting, let's see, 166.693 moles of carbon, right? Let me move this over. This other one has a unit again of moles of carbon, right? Because that's how much we used up. All right, so now we have to convert this back into grams. So we have 166.693 moles of carbon. We want this in grams of carbon, right? So we're going to multiply by the molar mass here, 12.01 grams of carbon for every 1 mole of carbon. And we end up getting 2,000. Let's use 3 sig figs here. So just 2001, that ends up being 4 sig figs here. We're just going to go with 2001. So 2001 grams of carbon are used up, or sorry, remain, not used up. Okay, so that's it for this one. There are some bonus questions here, so we'll quickly go through this. It says, in order to make an aqueous solution more concentrated or higher molarity, what would one need to do? Right, what you need to do is, right, you want to remove solvent. Right, the less volume of your solution, right, if we're looking at this, M is equal to moles over liters. 2 ways you can increase this. You add more moles of something to make it more concentrated. It makes sense. You're adding more stuff. Or you remove some of the solvent, right? The solution in the solution to make it more concentrated, right? It's like evaporating water. If you have salt, if you've ever done it, right? You have salt water, you sprinkle in a bunch of salt, evaporate some water, it gets more concentrated, right? You'll start seeing salt precipitate out at a certain point. Okay, so you remove solvent from the solution, right? If you add water, you're making it less concentrated. If you add solvent, you're making it less concentrated. I guess technically if you add water, if water is the solute, then it becomes more concentrated, but we're assuming that's not the case. So C says remove solute from the solution, and again, makes it less concentrated. You're removing moles of something from the solution. And then E says remove solution from the solution. So if you remove solution, you're not changing the concentration, right? You're just taking some out, but all of it is still uniform. You just have less of the same concentrated solution. Right? You need to remove the solvent. Right? What is doing the dissolving, right? Change the overall liters of your solution without changing the moles of solution. So for part E, again, you're taking moles out and you're taking liters out of your solution. So it doesn't change anything. All right, next says, which of the following is not a diatomic under standard conditions? So H2, C2, F2, Cl2, and N2. The answer here is going to be C2. Odd. I think my pencil may have just died. It did not. Okay, give me 1 second, having a few technical difficulties here. Okay, pen is back online. So carbon. Carbon is not typically diatomic under standard conditions, while these other ones are. Next is, what is the concentration of chloride in a 0.100 molar solution of aqueous ferrous chloride? So ferrous chloride, right? Ferrous chloride is FeCl2, right? It's iron 2 chloride. So if you know that, right, you know that there is twice the amount of chlorines, assuming it completely dissolves, twice the amount of chlorines as there are full molecules of, right, ferrous chloride or iron 2 chloride. So if it is 0.1 normally, right, for the whole compound together, if there's 2 chlorines in that whole compound, it doubles, right? So it's 0.200 molar, right? You could go ahead and convert this into moles and back to molarity. Now you don't have to. The reason why is because this is all in the same solution, right? You're not adding anything, you're not adding volume to this. So it's all in the same solution. So that's why I didn't convert to moles here, right? You can just leave it in molarity. And you're not adding volume specifically or taking away. So it's going to be twice as concentrated, again, 2 chlorines. All right, next it says, question, an excess of aluminum foil is allowed to react with 225 milliliters of HCl that contain 18% HCl by mass. What mass of H2 is produced? Okay. And it says, regarding this question, what missing piece of numerical information is necessary in order to solve this problem? So they give you the milliliters, right? So you can, you could potentially use the milliliters to solve for moles of HCl, right? To write your balanced reaction equation. But you would need molarity, right? You would need the concentration. Now they tell you that it's 18% by mass. So you can't use milliliters. You wouldn't use it, right, to solve for moles here, right? If you're given the concentration, because you're not. Instead, you're given percent by mass. Now, milliliters or volume is in 2 equations that you know so far, in molarity and in density, right? So if you had the density of this, you could find the total mass, right, of this solution that is being used, and then you could take 18% of that, and then you would have your amount of HCl being used, and then you could convert that into moles of HCl. And then again, then you could convert those moles into H2 being produced, right, with your balanced reaction. So the missing piece of evidence here is going to be the density. Actually, could be 2 things here, right? The density and the molarity, right? Because again, if you have the density, you could go ahead and solve for the mass, take 18%, you have your HCl, convert that into moles, or you could use the molarity and then go ahead and solve it that way. So actually two answers here for this question. All right, next is, which of the following transition metal cations have both +2 and +3 as common charges? So we have cobalt and chromium, iron and silver, copper and chromium, scandium and calcium, and lead and gold. So let's get rid of some of these. So silver does not have a +2 and 3 common charge. Silver is commonly +1. Calcium is a +2, right? It's not, doesn't have a +3, right? We're looking for both +2 and +3 common charges here. So another one we can eliminate is this lead and gold, right? Gold is typically a +1 charge, and copper can also be eliminated, right? It's 1 and 2. So that leaves you with cobalt and chromium. Next, it says, which of the following compounds would most likely contain a metal as one of the elements? So A, molecular, B, aqueous acid, C, organic, D, ionic, or all the above, right? So ionic are going to contain a metal as one of the elements, right? Most likely. Organic doesn't necessarily mean there's a metal. Oftentimes there's not, right? It's usually just carbon, oxygen, hydrogen, nitrogen, phosphorus. Aqueous acid, right? HCl, there is no metal, and so on. So ionic is going to be the one to most likely contain an element. Not always, right? But most likely. Next, it says, if the percent yield is 82.0%, how many grams of silicon is needed to make 105 grams of chromium by the reaction 3 SiS plus 2 Cr2O3, and so on and so forth. Okay, so you know that your percent yield is 82%. Okay. So if your percent yield is 82%, right, theoretically, you should have made more, right? So we're going to go off of what should have gotten, essentially. So for your percent yield, right? Wait, let me double check this. 105 grams of chromium. Yeah, so we're going to prepare to make more, right? So if you're only getting out 105 grams of chromium, we need to make more if we're only getting 82%. So if I do 105 grams divided by 0.82, right, then that'll give me how much I'm aiming for. So I'm aiming for 128.05 grams of chromium. Right, if I aim any higher, I'm going to get more than 105. If I aim any lower, I'm going to get less, right? Because I'm only yielding 82% in the lab. So now what I can do here is essentially use some stoichiometry, right? First, what I want to do is convert this into moles of chromium so I can figure out how many moles of silicon I need. So how many moles of chromium do we have, right? It's 52 grams of chromium for 1 mole. So we should end up getting 2.46 moles of chromium. Now we want to convert this moles of chromium into moles of silicon, right, that I would use for this reaction. So 2.46 moles of chromium, right? In this balanced reaction, I get 4 moles of chromium for every 3 moles of silicon used. Right, looking at the coefficients here. And I should end up getting 1.85 moles of silicon. However, that's not what I want. I want grams of silicon here. So 1.85 moles of silicon. And we're going to multiply by the molar mass, right? The molar mass of silicon here is 28.09 grams for 1 mole. And then you end up getting 51.9 grams of silicon. And that is your answer, right? So the answer is A here. All right, next, last one. It says the reaction below is 0.20 moles of N2 and 0.90 moles of H2. How many moles of H2 gas will be left unreacted after the reaction has gone to completion? Okay, so it is nice that they are telling us that, right, N2 is our limiting reactant. Now, to double check this, right, we need to make sure that this is balanced. This is not balanced. It's reaction. So what I want to do is balance this, right? I'm going to put a 2 here. So I have 2 nitrogens on the right and on the left, and I'm going to put a 3 here. So I have 6 hydrogens on each side. All right, now what I want to do, right, is this. I know nitrogen is the limiting reactant. So let's see how many moles of hydrogen I use up. So for every 1 mole of nitrogen I use from our balanced equation, I use 3 moles of hydrogen gas specifically. So I end up using 0.60 moles of H2. All right, so what I'm going to do is 0.90 moles of H2 minus 0.60 moles of H2. And I'm left with 0.30 moles of H2. And that is the answer, C. Okay, so if you've stuck it out this long, I hope that helps. I'm going to go ahead and do the last question. Again, I don't think, or sorry, not the last question, but that balancing question for number 7. Would not worry about it if you do not understand it. This one is going to be just a lot of algebra, setting up a system of equations, and I don't expect this to be on your test. So this would be quite a lot of work, and I actually don't know an easier way to balance this. So hope that helps. If you're watching and if you're going to stay tuned, then just bear with me for the next 15 minutes. All right, put that back there. All right. So I have this reaction right here. All right, how do I balance it? So what I can do here is I'm going to label these coefficients as variables A, B, C, D, E, F, G. Now what I'm going to do is for each element, write a system of equations that has to be, or an equation that has to be true, right? So start with potassium here, right? So the potassium, right? I'm looking at both sides here in the coefficients. So for potassium on the left side, right, I have 1 times A from this one right here. So 1 times, right, there's 1 potassium per molecule, and I have A amount of molecules in this balanced equation. So 1A plus 1B, right, plus 2D. So there's 2 potassiums here, right, times D. D is some integer. And this has to be equal to, oops, oh, I did not see the arrow. Yes, sorry, 1A plus 1B has to be equal to 2D, right? I'm actually going to write this in blue so it's easier to see. So these two things have to add up, right, to this thing on here. That's what this equation is saying. So 1A plus 1B has to be equal to 2D, right? The 2 comes from the potassium, how many potassiums are in that molecule next to the D coefficient. All right, next, if I use manganese here. So for manganese, again, same thing here. I have 1A, right? There's only one on the right, or sorry, on the left here. And I have 1E on the left, right, mixing these up. So 1E on the left, right? There's 1 manganese, the coefficient is E. So for every E, I have 1 manganese. So A, you can see here, has to be equal to E. And we're going to do that for all these coefficients. So next, right, we have manganese. Let's do oxygen. So for oxygen, right, there's 4 in that first one. So 4 times A, 4 oxygens per A. For C, there are also 4. So this is for C. For D, right, there's 4 oxygens. For E, there are 4 oxygens. And then for G, there's 1 oxygen. Now let's go ahead and go to iodine. So for iodine, right, we have 1B. There's 1 iodine in Ki. And then we have 2F, right? There's 2 iodines in I2. Last but not least, oh no, not last but not least, we still have sulfur and hydrogen. So sulfur, right on the left here, we have C. There's 1 C. And then on the right, we have 1 D and 1 E. All right. Last but not least, we have hydrogen. So for hydrogen, you have 2C, and then from that H2SO4, and at the end, you only have G, right? So then it's 2G. You can see here that C equals G, right? For the coefficients, they have to be equal here. Now, how do you solve this, right? It's just a whole lot of math and substitution. So what I can say here again is C is equal to G. Over here, A is equal to E. All right, we got the easy ones. And why'd I put an arrow here? Should be an equal sign. So let's see. Is there one that we can just get rid of right now? So many equations here. So if I go ahead and plug in, thinking A into this one, no, then you still have G. No, so you get rid of G to C. And you have D in terms of A and B. So if I were to plug in A here and C here, I could then get A and C and D related. Now I'm trying to see if there's a way that we can get rid of D here, because that would be great. Oh, we can. Look at that. So we can get rid of the D with this equation with S. So I'm going to go ahead and bring this down here, right? Where E is equal to A, where G is equal to C, and where D is equal to C minus E, right? And we know that E is A. So this is C minus A. So we have 4A plus 4C is equal to 4D. So that's 4C minus 4A plus 4E, which is 4A, plus 1G, which is C. All right, so you can go ahead and cancel out your like terms. You get 4A plus 4C is equal to 5C. And then we end up getting C is equal to 4A. Oh, nice. Now we got C out of the way. So that's good. And then we'd have to do some more rearrangements here. Yeah, so essentially, what I'm going to want to do is get everything in terms of some one variable, and then just pick a number for that variable. So I have C is equal to 4A. I'm just going to write these all on the side. Right, I know that C is equal to G. So I also know G is equal to 4A. I know that E is just equal to A. Right, so I'm still missing the relationship for B, D, and F. So we have to figure out a way to find those, right? So we know B and F are related. So if I can find one of those, right, probably B, then we'll be in better shape here. So right, we have two formulas with D. We should be able to use the elimination method here, right? So I have these two formulas with D, correct? So what I'm going to go ahead and do is use elimination. I'm going to go ahead and do it down here. So 4A plus 4C is equal to 4D plus 4E plus 1G. I'm going to subtract the one up top, right, the one that we did for potassium. So I'm going to multiply it by 2. So this is going to be 2A plus 2b is equal to 4d. Again, this is algebra, so elimination method from algebra. These d's go away, and I'm left with 2a minus 2b plus 4c is equal to 4e plus g. Now, Now what I can do is I can go ahead and replace everything that's not b with a, right? Because I have all my relationships up here. So c is 4a, right? So I can say 2a minus 2b plus 4 times 4a is equal to 4e is what? E is a, is equal to 4a. That should be a plus g plus 4a, right? Because g is also 4a. So we're going to go ahead and add our like terms here. So this is 2a. Actually, so on this whole side, it's going to be 18a minus 2b is equal to 8a. Subtract 8a from both sides and add 2b to both sides. So we get 2b is equal to 10a, or b is equal to 5a. So I have another relationship here. B is equal to 5a. I know that f is equal to, sorry, I know that b is 2f. Wait, yes. So I know that, let's say this. So if b is 5a, that's 2f, right? F has to be 5 over 2a times a. And then I think that's it. So we have b, c. We don't have d. Actually, we do have d. So what we can do is plug it back in here, right? To this first one, 1a plus 1b is equal to 2d. 1 or just a plus b equals 2d. And I know that b is 5a. So a plus b is equal to, sorry, what? A plus 5a is equal to 2d. And then I end up solving for d is equal to 3, right? 6a equals 3d, sorry, 2d. And then d is equal to 3. All right, so I'm going to go ahead and move this down. A, B, C, D. D is 3a. Okay, so now that we have everything done, right, what I'm going to do is pick a number here, right, for a. So if I go ahead and let a be equal to some number, all these other things are going to fall into place. Now I'm going to let a equal 2. Why? The reason I'm picking 2 is so that this thing right here is not a fraction, right? If I pick a equals 1, it has to be a whole integer. If I pick a equals 1, I'm going to get 5 halves for a coefficient, and I don't want that, right? So I want to pick a better number, right? You could do 4. I want to pick some multiple of 2. So I'm going to just say a is equal to 2. So if I do that, a equals 2, b equals 10, c equals 8, d equals 6, e equals a 2, f equals 5. Now I can finally go ahead and take all of these and plug it in here. So a is 2, so 2, 10, 8, 6, 2, 5. I totally forgot about G. Uh-oh. Did I go out of order here? So A is 2, B is 10, C is 8, D is 6. E is 2. Okay, so I did just miss G. So G is also 8. All right, and then that is your answer. So that's how you can do that one. Again, I would not worry if you don't know how to do this. It's a lot of algebra, take way too much time on a quiz or exam to actually do this whole thing. So I would not sweat it. All right, so that's it for this one. I hope that helps, and I will see you in the next one.